we end with finding strongly connecting components. We talked about topological sorts, and now we talk about other tasks that can be solvable with algorithms that names as Ford-Fulkerson algorithm, and it contains, of course, BFS and DFS in it. So let's start to talk about it. There is other class of graphs that we need to explore. I can draw example of flow network to understand definitions. For example, if we have some vertices, we can represent them in the plane that, for example, each edge starts with one vertex, go to the other, like other directed graph. And of course, graph can have directed cycles, for example. Okay, and as you can see on the slides, there are two distinguished vertices, source and sink. And we say by definition that source has no input edges and sink has no output edges. Okay, and here we can draw any directed graph. Then second important point of this class of graph is that each edge has capacity. It is function from edges to real numbers that bigger to 0 or equal to it. It's any different functions, but of course we say that algorithm for Ford-Fulkerson algorithm works with only integer capacities. Okay, and for example, I can draw capacities of this graph. For example, 5, 4, 3, 2, and of course we can have edges in both directions, and they can have different capacities. For example, it can occur in our graph. And okay, and this graph can be named as flow network. But of course, we need to understand what is flow, and you can see definition of it. Yep, it's similar to capacity. It is to function from set of edges to the real numbers that bigger than 0 or equal to it. But there are three conditions that we need to be met. First, very important that flow cannot be bigger than capacity of edge. It's understandable. For example, you can try to understand flow network as a transport network or flow network in the houses that we have. Yep. Or for example, you can represent the vertices as cities and edges like roads between cities, and you have constraints with constraints of the roads of your country, for example. Yep. So it is understandable that flow can be bigger than capacity, and we say that every edge has a flow in one direction equal to minus flow in other direction, and of course we think about it like our graph has edges between any two vertices, but if we don't draw edge, then we say that this edge has capacity equal to 0. Okay? So if, for example, we can say that there is no edge between source and sink, so this edge has 0 capacity. Okay? And for example, we can say that capacity of the edge BA is equal to 0. Okay? Because we don't draw it. So, and the last condition is equal that we have no troubles in the vertices because of conversation of flow. Yeah, we say that if we has flow, we can sum all flows that input in vertex and sum of all output flow, and it must be equal. Understandable? Yeah. And for example, I can draw some flow. For example, two. No. 1. It's equal to 1, 2. 2. Then, for example, 2. 1. 1. 2. 1. 1. 1. 1. 1. Oh no, we need to example this. Okay. Red numbers is equal to flow of the edges. I can write.
The black numbers is just random numbers or?
No, it is capacities of the edges. Numbers are flow of. You get a flow network initially, and flow network has capacities of each edges. you don't need to understand what is the capacity of the edge. You get it like all of the graph. Yeah, yeah, yeah. It contains in input of the data. Oh,
So the flow will be
here?
that, yes.
Yep. And what?
The flow for will be
Oh,
there is variable like the
do we need to get flow in the other direction?
I mean the flow will be -2.
Here?
Ah.
No. Flow is equal. Flow is the function of the edge. And we can say that, for example, I need to name these vertices. For example, it's C and D. We can say that edge CD has flow equal to 2, and edge DC has no flow, or flow is equal to 0. Oh, okay, about, yeah, you're right. We can say that it's equal to -2 too. Yeah. So, and black numbers is equal to capacities, okay? And so we can say that if we sum flow of the edges that out from the source, it's equal to 3, and it is value of a flow. Okay? We say that value of flow is the sum of the flow leaving from the source. Or for example, conversation. Oh, for example, you can see if we
What is P?
T is the
Yep. For example, for D, we say that sum of flows that starts in D and ends in V. For example, here we can say that this edge has capacity equal to 0 and so flow equal to -2. So if we sum all of the edges incident on vertex D, it will be equal to 0.
Yes.
But of course, if we see about this source or sink, yeah. Okay. So about Ford-Fulkerson algorithm. Oh, it's very big network to use it, I think. But I can draw one thing that says that this flow is the maximal flow in this network. You can see that if we cut our graph in two parts, this and this part, there are two edges between them, and sum of the capacities of these edges equal to 3. And our flow has value equal to 3, 2. So I can say that this cut names as minimal cut of the network, and our flow names as maximal flow. And there is a theorem I can write it that in the any flow network, minimal cuts is equal, capacity of minimal cut is equal to value of the maximal flow. Any flow. Any flow network, maximal of values of flows is equal to capacity of the minimal cut. And I will say about it in some minutes too. But now we can see that if we have flow in the network and have capacities, we can draw other network names as a residual network that can be built by the algorithm. And I get other example to this. For example, if we have this network with capacities equal to 1. Firstly, and you can see on the sides, first step, we say that flow is equal to 0. Then we build residual network. We get no. Oh, and can I copy it? Do you know how to copy this? No.
Here,
Where?
the fourth one, yes.
Fourth?
Maybe
No.
in the top of this one. Yeah, if you touch again. Or
next
next to the color. Yeah.
Oh. Nope. Okay, I will draw it Okay. And in the residual network, we say that there are edges, there are forwards and backwards edges. And I now say how to compute it. For example, about forward edges. We have for each edge capacity of this edge, and we have flow that go through this edge. And capacity minus flow is equal to the number that I need to write on the edge. For example, it's equal to 1. And equals 1, 2. Okay. And in the other direction, I need to do the same, but of course, I say that capacity of these edges equal to 0. Yep. So I write these numbers of edges and this too. And I say that it is capacities of edges in the new graph that we name as a residual network. Okay? So I try to find a path from the source to sink. For example, I can draw. Can find this path. And if we have an augmenting path, we say that this flow isn't the maximal flow of the graph. Then we say that we can increase our flow at this path in the flow. And then we get new flow in our network. We draw our graph with capacities. And we increase our flow. Yep. Value of this now is equal to 1. It's bigger than value of this flow. Okay. And now it is important that we have the augmenting path in the residual network for this flow. You can see that if I draw it, we have all of the edges. And as I said earlier, that we have these capacities of these edges, and for example, for this we have 0, for this we have 0, for this we have 1, 1, and 0, 2. Yep. but we have backward edges. And now we have 3 edges with capacities equal to 1. This backward edge has capacity equal to 1. This, and this has capacity equal to 0. Okay, and now we see that we have path from the source to the sink through these edges. And we can use backward edges too. And if we use backward edges, it means that we need to decrease flow through this edge. And now we can draw new new network. We have the same capacities. And now we have flow that has value equal to 2. Yeah? We can see that we increase value of the flow. And if we try to draw residual network, and write all the capacities. Yep. For example, 0, 0, 0, 0, 1. Oh, nope. 0, 0, 1, 0, 0, and backwards edges, it's equal to 1, 1, 0, 1, and 1. And of course, if there are no capacities on the edges, we can say that we have the path from the source to the sink. Yeah? But we need to get edges with non-zero capacities in the path. So we say that there is no paths from the source to sink that contains only edges with capacities bigger than 0. So we can try to find which vertices we can reach with paths contains only edges bigger than 0, and we say that there are no 1 vertices that we can reach from the source. So it is minimal cut of the network. And it is 3 steps of the algorithm names as Ford-Fulkerson algorithm. And for example, it is proof of the theorem that I write here. Because when we get the maximal flow in the residual network, we can get minimal cut of the network capacity of it equal to maximal float. Okay, but there are two problems with this algorithm. Go to the slides and about time complexity. Of course, we can use DFS or BFS that we researched earlier to find augmenting path. And we spend only O from number of edges time to find the path from the source to the sink. But we can draw an example when time complexity of this algorithm is equal to number of edges multiplied by maximal of capacities of the edges. For example, if we can draw the similar graph, but the capacity the capacities of 4 of these edges will be equal to 1000, for example. And this capacity equal to 1. Then we can try to use a Ford-Fulkerson algorithm, and in each step we increase our flow only by 1. And then we get 2000 steps of the algorithm. Yeah, it is of course of the big capacity of the edges. Okay? And I can... Do you understand this?
No.
Nope.
No.
Why it is equal to 2000 steps? Okay, go back to this example. We can get augmenting path through the middle edge in each step. And then we say that we can increase only by 1, because my minimal capacities of edges that contain in paths that go through the middle edge is equal to 1. So if we increase our flow with the augmenting path that go through the middle edge, we can increase only by 1. Of course, if we get this augmenting path, we increase our flow by 1000, then increase by 1000, and we have 2 steps. Yeah. But if we have a random random choice of the augmenting path, we can, for example, choose in each step paths that go through the middle edge. And then when we get we get 2 steps and increase flow that go through the upper path and go to through the lower space path by 1, because of this 2 steps or 3 steps of the algorithm. And then we get flow equal to 2, then we get 2 steps of the algorithm. Then we repeat this, and we get a flow that will be equal to 4, then will be equal to 6, etc. I need to repeat it too. Yep. No?
I think there are several things that are not understandable. What is
Okay.
augmented path and what is
Augmented path is the path in the residual network that contains only edges with capacities bigger than 0, that starts in the source and ends in the sink.
and what is
Residual network, if we have flow network with flow, we say that residual network is equal by vertices to the flow network, and each edge has capacity equal to this. It is the new capacity of the edge E in residual network. So we see flow is equal to 0, so capacities of the edges equal to capacities in this network. But on the second step, we see we have not 0 flow, and say that, for example, for edge that connect these two vertices will be equal to 0, because it is the difference between capacity and flow. Understandable? So, for example, if we try to understand it, yeah, we get augmenting path, and initially we have 0 flow. Then in one step we get flow that will be equal to 1. As in the previous example. Then we increase by increasing flow through this edge, and decrease flow through this edge. And we get new flow. Value of this flow is equal to 2. But of course, we need to repeat the steps 2000 times to increase flow to 2000. Do I need to make next 2 steps of this algorithm? No? Better to draw it. No? Who understands it? You? Other? Understand? Okay, and questions? Can you make a question about this? Do you understand Ford-Fulkerson algorithm? Nope. I need to repeat it. I need to repeat. Okay. Do you understand what is the flow network?
Yeah. The definition, yes.
This is definition of level network. We have directed graph with capacitors, and we have two distinguished processes, source and sink. Okay. Then, do you understand what is the flow?
Yes.
Understand. I draw it like red numbers of the edges. So then if we have flow network with flow, we can draw residual network by the algorithm. Yep. We need to make a residual network and find the augmented path. How we can draw this residual network? We draw vertices like in the initial graph, and then we say that edge in the residual network has capacity equal to difference between capacity of this edge and flow. It is understandable too. And okay, we build residual network. Then we try to find path in this residual network from the source to sink that contains only edges with capacities bigger than 0. For example, in this picture we have these 3 edges that connect source and sink and has capacities bigger than 0. So we say that we can increase our flow using this path, and to increase edges flow on these edges, on this.
Okay.
You can see
Yeah.
by the augmenting path.
Yes.
Then we repeat our building of residual network, and we see there is other path from source to sink that contains edges that have capacities bigger than 0. Yep. So now we have this edge that make orange capacity. I mean that this color is equal to backward edge, and it means that we need to decrease flow through this edge, not to increase, to decrease. And we see that we can increase all flow by 1, but we need to increase flow through this edge by 1, decrease flow through this edge by 1, and increase flow through this edge by 1 too. So we get this picture. Yeah? We don't touch this edge and this edge. We decrease flow through this edge by 1 and get 0 flow, and we increase flow through these edges and get now 1 and 1. Yeah? Yep,
Why do we have 0 as flow in the middle?
in the middle.
Yes.
Because here we have flow equal to 1. And we say if we have backward edges on the path, we need to decrease flow on the edge in the initial graph. And it is very important that to increase value of flow, we need to decrease flow on the current edge, and increase on the other edges. And now we have flow from the, flow that has a value equal to 2. And if we draw residual network, we see that there is no path from source to the sink. Do you see? Okay. And then we say that it is the maximal flow in the graph. Okay? And if we try to repeat these steps to this graph, we get 2000 steps, because one step increase our flow only by 1. And the maximum flow is equal to 2000. So we have 2000 steps of the algorithm. And it is bad, of course, because we want to get time complexity that depends only number of edges or vertices. Does not depend to the capacities of it. Okay, and of course there is improvement of this algorithm, names as Edmonds-Karp algorithm, that runs in this time. Okay, so if you want, you can Google it and find this algorithm too. It is equal, very similar to Ford-Fulkerson algorithm, but has different understanding of what which the augmenting path we need to use in the residual network to increase our flow. Because we understand if we find this path in augmenting flow in the residual network, we increase our flow by 1000. Then we increase by this path by 1000, and we have only 2 steps. It's better than 2000 steps, of course. So it's about Ford-Fulkerson algorithm, and some information about dualities. Theorem that I write sometime before is equal to this theorem, yeah. And it is one of the it is one of the duality theorems, and duality is an important method in optimization problems, because for example, in optimization, in the optimization, there are a lot of exercises to get infimum of some functions, for example. And there is method to get quick lower bounds of this function names as duality, and it is very important transformation that we can get primal primal problem, and to understand how we can bound this problem, we need to compute this number, and it is dual problem. And in some cases, it is simpler to compute dual task than primal task. And for example, in this case about flow and cut, about flows and cuts, we say that if we has flow network and we want to understand what is the minimal cut of this flow network, we can get maximal flow, and then, as in this task, if we have maximal flow that go through the graph, we say that we can get minimal cut, and it is two duality between two tasks. First, to find maximal flow, and second, to find minimal cut. And it is important to understand that we have this method, and maybe if we have time in the end of our course, we will talk about duality and other linear problems in the programming that we can solve with duality method. So that's all about today's topic. If you have any questions, you can ask, and you too. And if there is not any questions, we can end our lesson.
What is the minimum cut?
What is the minimal cut? Okay. We say that if we have a flow network, we can part our graph into parts and say that cut is equal to value of the cut is equal to capacities that go from the left part to the right. For example, here we see not in the residual network, we need to get here minimal cut. We see there are two edges, and sum of these edges equal to 2, and it is value of the cut, and we say that if we have flow network with maximal flow, then minimal cut of this network we can build by connectedness of a residual network. we say that from source we cannot reach any other vertices using edges with capacities bigger than 0. So we say that minimal cut of this network is equal to dividing set of vertices in these two paths. And for example, for the previous, we see if we get residual network from the source, we can go to A, because 5 minus 1 is equal to 4, and we have edge from S to A in the residual network that is that has capacity equal to 4 bigger than 0. And we see that 4 minus 2 is equal to 2, and we can go from source to the B using this edge in the residual network too. But in the residual network, this edge and this edge have capacities equal to 0. So we say that left part of this cut is equal to this subset of the vertices, and right part is equal to this subset of the vertices. And cut in the flow network, it is dividing set of the vertices into two parts. One part contains source and one part contains sink. And we say that it is minimal if it has minimal value. And value of the cut is equal to sum of the capacities capacities of the edge that start in the left part and end in the right part. Okay, we see that sum of these two capacities, if we sum it, we get 3. Yeah, and it's equal to flow that we have in this network. And of course we said that each cut and each flow has values or have values such that value of the cut bigger than value of the flow. It's important that it's the theorem and very simple statement that for each flow with value equal to F, and for each cut with value equal to C. We can say that F not bigger than C. It names as it names strongly duality, and it names as not strongly duality. I forget how to translate it. Weak duality, yeah. It is weak duality. So if we find such flow and such cut that it is equality, then we can say that such flow is the maximal flow in the graph, and such cut is the minimal cut of the graph. And for example, in this case, we say that we find minimal cuts because this value equal to 3 and value of this flow equal to 3 too. And then we say we get equality of this in this moment, and then we say that it is minimal and maximal cut and flow respectively. Understandable?
Yes.
Okay. So it's about duality. I think we repeat it, of course, if we get the time to talk about duality in the end of our course. Okay, and other questions? Nope. Oh, yep. Yes.
From the source.
Yep.
I mean, yes, this one. From source to sink, it's
Mhm.
not a path because the flow here is 0.
Yep. Yep. Because capacities of these edges equal to 0. Yep. And of course, if we have, for example, capacities of the initial graph equal to 2, this, and we have paths in this residual network from source to sink through these edges. So we say that it is not maximal flow, and we can increase by this augmenting path. And we will repeat our steps of the algorithm. Okay, other questions?
So we repeat till we get no path.
Yeah. And when we have no paths in, we have no paths in the residual network from source to the sink using edges with capacities bigger than 0. So we say that it is maximal flow, and we can build minimal cuts of the flow network. Okay. Other questions? Nope. In the chat? No other questions. Okay, that's all.